This lecture is part of an online course of multivariable calculus, and I'm going to talk about conservative vector fields in a space. So let's take a vector field F that is in a space. So it has three coordinates, pi plus qj plus rk, where p, q, and r are functions of x, y, and z. Okay? So then we say that the vector field F is conservative if it is gradient of a vector, of a function. So gradient of a function f is partial derivative of f with respect to x, partial derivative of f with respect to y, and partial derivative of f with respect to z. So the question is that what is the condition of being conservative? Conservative. Well, let me give you a recall that if the vector field F has just two coordinates pi plus qj, okay, so if the vector field F is just defined on the plane, then it was conservative if we have fx and fy in here, if p is equal to fx and q is equal to fy. So based on that, if p with respect to y is equal to q with respect to x, which means that fxy, then it's equal to fyx. So as you see, that was the condition for a vector field in the plane to be conservative. Now, a condition for a vector field to in a space to be conservative is this. I'm gonna say that, you see, a function f is defined on three variables. So fxy is equal to fyx, okay? And I know that based on here, p is equal to fx, q is equal to fy, and r is equal to fz, okay? So this one is here is p, and fy in here is q. And so based on that, I can say that p with respect to y should be equal to q with respect to x. This is the first condition that we need to check. Then fx z is equal to the partial derivative of f with respect to z and then x. Okay, let's see. I'm gonna make my pen smaller. fx is p, fz is r. So based on that, p with respect to z should be equal to the partial derivative of r with respect to x. This is the second condition that I need to check. And then f of y with respect to z should be equal to the partial derivative of f with respect to z and then y. Okay, so f with respect to y is q, f with respect to z, where's that? It's here, it's r. So q with respect to z should be equal to r with respect to y. This is the third condition that I need to check. So let me just clean it up a little bit in here. So these three conditions are the conditions that I need to check and make sure that if these conditions are satisfied from my vector fields, then my vector fields is conservative. And now how to find the potential function is like as before in the plane, but it has 3 steps because we have 3 variables. So let me explain everything in one example. So example is this. The vector field F is yzi plus xz plus 2yj and xy minus 2zk. Is it conservative or not? And find the potential function. Okay. So for the solution, this is P, this is Q, and this is R. Okay. So I know that P with respect to Y should be equal to Q with respect to X. Let's check. What is P with respect to Y? Partial derivative of P with respect to Y is just Z. Partial derivative of Q with respect to X is just Z. So these two are equal to each other, so we're good now. Then P with respect to Z should be equal to R with respect to X. So P with respect to Z is equal to Y, and R with respect to X is just equal to Y because Z is just a constant, so this part would be 0, so it's equal to Y. So we're good up to now. And then Q with respect to Z should be equal to R with respect to Y. R with respect to Y. So derivative of Q with respect to Z is just X. Is it equal to derivative of R with respect to Y, which is X? Yes. So all of them are satisfied. So we say that yes, F is conservative. Very good. Now I need to find its potential function. So potential function. So for finding the potential function, what I need to do, I need to solve this one. I need to say that I need to find the function f such that derivative of f with respect to z, with respect to x, is equal to p, which is this one, yz. Derivative of that function with respect to y is equal to my second coordinate, xz plus 2y. And then derivative of f with respect to z is my third coordinate. F with z is x, y minus 2z. Very good. Let me call them a name. This is number 1, this equation is number 2, and this equation is number 3. I'm going to start with equation 1, which is equal to what? Fx is equal to yz. Now I'm going to take the integral of that with respect to x. So the integral of partial derivative of f with respect to x dx is the integral of yz with respect to x. So on the left hand side in here, the antiderivative of a function, so I get my function f, which is a function of x, y, and z, because the function f is in a space, has 3 variables. And then with respect to x, these two are constant, so these two constant, and then, so actually let me write this like that. I'm gonna bring the constant out. Constant is just because I have the integral with respect to x, and then I have 1 dx, so it is just x, right? Plus the constant c. Now you see that the constant c is just because we are taking the integral with respect to x. The constant c here is a function of the other two variables. We were taking the integral with respect to x. That's why the constant is a function of y and z. Okay, very good. Now we found our potential function. All I need to do is to find g, right? So what I'm gonna do to find g, I'm gonna differentiate with respect to y, and then with respect to y, what do I have? Derivative of f with respect to y is f of y. Derivative of this part with respect to y is xz. And then derivative of this one with respect to y is what? Is partial derivative of g with respect to y. It is not g prime, it is not dg dy, it's curly. It's just because g is a function of two variables, I'm taking derivative of that with respect to y. Okay, so based on equation 2, I know that if y is equal to that. So now using equation 2, I have what? It's equal to, using this equation, it's equal to xz plus 2y. Okay, and so xz in here is going to be cancelled out with xz in here, and that's why I get partial of g with respect to y is equal to 2y. Very good. Now I'm gonna take the integral of both sides with respect to y. I have g with respect to y in here. I use another notation for this, and then I'm taking dy, and it's equal to the integral of 2y dy. I'm gonna make this one black. Okay, and so I have antiderivative of a function g with respect to y. That's why I get the function g of y of z, the whole function. Don't forget that g was like that. It's equal to the integral in here. It would be y squared plus a constant c. But the constant c here is actually not just a number. It's a function of z. It's just because g was a function of two variables. We took the integral with respect to just one variable. So I have h of z as the constant in here. Okay, I'm gonna move everything. Oops. I'm gonna move everything a little bit so that I have more space in here. Very good. So if you want to check your work, I'm gonna say that if I take derivative of that with respect to y, I need to get to this part. Derivative of g with respect to y is g of y. Derivative of that with respect to y is 2y. And then derivative of h of z with respect to y is 0, because h of z is a function of z, which would be constant with respect to y. So far, what do we have? So far, we have this. F of x, y, and z, x, y, and z is equal to y, z, x plus g of y, z, which we found it in here, which is equal to y squared plus h of z. Perfect. Now I need to find h of z, and notice that I used the first equation, I used the second equation in here, but I haven't used the third equation. So now it's time to differentiate the function that we found, which is with respect to z, to use the third equation. So let me do it. So I'm gonna differentiate f with respect to z. Okay, so what do I have? I have f of z. Derivative of here with respect to z is just yx. Derivative of y squared with respect to z is 0. Derivative of h with respect to z is just h prime of z. It's just because it's a function of just one variable. Derivative would be like a prime notation. And then based on equation 3, I know that f with respect to z is equal to that. So that's equation 3. And I know that this is equal to xy minus 2z. Very good. Now let me cancel these two. And so h prime of z is equal to negative 2z. And I'm gonna take the integral of that with respect to z. Okay, so what do I have? I have the integral of h prime of z. dz is equal to integral of negative 2z dz. Okay, it is what? Antiderivative of derivative of the function h. So it is h of z. Derivative of that with respect to z is negative z squared plus a constant c. And notice that in here the constant c is a true number. It's a true constant. It's just a number. Let me write true number. It is not a function of something. Why? It's just because h was a function of one variable z, and I take the integral with just respect to z. That's why it's just the number c. Now let's see what we have so far. We have f of x, y, and z is equal to yzx plus y squared plus h of z. H of z is here. Negative, actually. Negative z squared plus a constant c. Perfect. That's the potential function. Now, if you want, you can check your work. You see? Take derivative of that with respect to x. I get just yz. Very good. It's p. Take derivative of that with respect to y is xz plus 2y, which is here. Take derivative of that with respect to z is just yx minus 2z, which is here. Okay, that's how we find the potential function. You need to solve fx equals to p, fy equals to q, and fz equals to r, the third coordinate, and then you just start taking the antiderivative with respect to x, and then find the constant c is a function of the other two variables, differentiate that with respect to the second variable to be able to use the second equation, and then you get a function of the third variable as your constant. Then take derivative with respect to the third variable, and then you find the constant as a number, put everything together, you find a potential function. It would be a little too many calculations, but it's not that much hard. All you need to do is just keep track of your c, of the constant c. That's it.